All right, let's dive right in. Today, we're talking about calculus sequences, and we're going to tackle one big question about these endless lists of numbers.
So here it is, the big mystery. Imagine an infinite list of numbers stretching out in front of you. Does that list eventually zero in on one single destination, or is it doomed to just wander around forever? That's what we're going to figure out.
Okay, so the official textbook definition is a little stuffy, right? A function whose domain is the integers. But here's what it really means. It's just a list of numbers. That's it. A list that has a specific order and goes on forever and ever.
Now, every single sequence out there has one of two fates. It either converges, which is a fancy way of saying it settles down and gets closer and closer to one specific number. We call that number the limit. Or it diverges. This is the wanderer. The numbers never pick a destination. They just roam around forever.
Okay, theory's great and all, but let's get our hands dirty with our first case study. This is where you really start to get it. We're going to start with a super common type you'll see all the time in calculus, the rational sequence. So, here's our first problem. I know, it looks kind of complicated with all those n-squareds flying around, but trust me, there's a really slick, simple trick to figure out exactly where this thing is headed.
Here's the game plan, and it is so powerful. You find the biggest power of n, which here is n squared, and you divide everything, top and bottom, by it. So, why do we do that? Well, look what happens. As n gets ridiculously big, think a billion, a trillion. What happens to 1 divided by a trillion squared? It becomes practically 0, right? Those little fractions just, poof, they vanish into nothing.
And after all that dust settles and those little fractions disappear, what are we left with? Just 3/2. And that gives us our destination, our limit, 1.5.
And since we found one single, concrete number that the sequence is marching towards, we have our verdict. This sequence converges. It found its home. Case closed.
All right, on to case study number 2. And I gotta warn you, this one's a bit of a classic trick question. This is where a lot of people get tripped up. We're looking at what's called an alternating sequence.
Now take a close look at that formula. You see that little -1 to the n part? That's our troublemaker right there. Its only job is to make the sign flip back and forth, from positive to negative. Let's see what that actually looks like.
So as we start plugging in numbers for n, you see the pattern right away. We get -0.5, then positive 0.66, then -0.75. It's just bouncing back and forth across 0. But is it actually settling down?
This is the absolute key. The size of the number, what we call the magnitude, is definitely getting closer to 1. You see it, 0.5, 0.66, 0.75, it's crawling toward 1. But the sequence itself can never land on a single number because it's forever jumping from the positive side to the negative side.
And for that reason, the verdict has to be, it diverges. See, to converge, you have to pick one destination. This sequence is trying to go to 2 places at once, +1 and -1, so it never settles down. It's a wanderer.
All right, let's tackle our third and final case study. This is another really important one, the geometric sequence. You'll see these all over the place, and luckily, they follow a really clean, simple rule.
So our problem is the sequence you get by taking 0.9 to the power of n. Just think about what's happening. You start with 0.9. Then you multiply by 0.9 again, and again, and again. Every step you take, the number gets a little smaller. But does it head towards a specific value?
And this right here is the golden rule for geometric sequences. It's like a cheat code. All you do is look at that base number, the r. If its absolute value, basically its size without any negative sign, is less than 1, it converges, period. If it's 1 or bigger, it diverges. It's that simple of a test. So let's just apply the rule. Our base r is 0.9. Is the absolute value of 0.9 less than 1? Yeah, for sure. The condition is met. And just like that, we have our answer.
So the verdict is in. It converges. And what's cool about this rule is we know exactly where it's going. Any geometric sequence that meets this condition is always heading straight for 0. Okay, so we've gone through our 3 case studies. Let's just take a second to recap the big takeaways from our investigation.
So for those rational sequences, the winning strategy was to divide by the highest power of n. For the tricky alternating ones, the key was making sure it settled on just one value, not 2. And for the geometric ones, it all came down to that super simple rule. Is the absolute value of the base less than 1? 3 different puzzles, 3 different keys.
We've unpacked the main ideas and walked through some classic examples. So now it's your turn to take the wheel.
You've seen the logic.
You've got the strategies in your toolkit now to figure out if a sequence finds a home or just wanders forever. So the big question is, what other sequences can you solve with this?
And hey, if you want to put these new skills to the test, the source we dove into for today, Baker's Math Class, has a practice quiz all ready for you. It's really the best way to make sure this stuff sticks.
Thanks for hanging out with me today. Go out there and hunt down some limits. Happy solving!